To be honest, I was way more time yesterday than I was practicing,
Like this view, and it goes on.
Does that work?
It should. It's not on right now. But that's how you switch. It pins somewhere close to your mouth, and then you put it in your pocket or.
Sounds good.
Yeah, that little button is the on-off.
Yeah.
There. This does not seem to be enough people. Okay.
Do we have a laser here? Or...
Yes, this is.
Okay.
I think we can just go to your There it is.
Yeah, there's a few slides before.
That's
So
why it's starting.
yeah, there we go. Sweet.
There's really not enough people. It's possible everyone has abandoned us. While we are hopefully waiting for more folks to join us for the remainder of the symposium, a reminder, if you are coming to the open mic tonight, that normally we are not, the general public is not allowed access to Space Telescope after 6 o'clock, but they're opening the doors for us from 7:30 to 8:30 p.m. You'll need to wear your badge to get access and just show that to security. And if you are after 8:30 p.m., they're going to be really grumpy with us. So very much try to be here before then.
There's a door right there to the outside.
Someone could. I'm not saying that I'm going to do that because I don't wish to be in trouble with my employers, but maybe someone could do that. I don't know. Please just try to be here before 8:30 is what I'm trying to say. Might wait just for Jen to get back, and then we'll just move forward.
She's not coming back.
If she doesn't come back, then I don't know. We're on our own.
There she is.
Okay. To not lose more time, I'm going to go ahead and get started. This is a dust and protoplanetary disk afternoon. So we're starting with protoplanetary disks, and our first speaker is Andreas, and I will give you a 2-minute warning and then shove you off the stage.
Sounds good. Thank you very much. So thank you to the organizers for having me here today. It's an actual pleasure. And today I'm going to be talking about a very peculiar chemical signature that we're detecting towards an embedded planet in the disk of HT 163296. We're making this discovery with ALMA, as some of you may have already predicted. But ALMA, gives us access to a number of other tracers for planet formation. This is probably the most obvious ones. This is millimeter continuum towards the disk of HL tau. And I will say this is a pretty revolutionary image. A decade ago, we got this one after ALMA started operations. And this really, marked this kind of turnover point in the field, because before this, we were kind of used to these kind of images, right? This same HL tau disk, same wavelengths, but just using a different interferometer. And so what people have been doing in the past few years is, okay, you have these kind of dust substructures, very prominent dust substructures in the disk, and then you can produce planet-disk interaction simulations and try to infer planet presence here, infer where the planets should be located and whether their masses should be high or low, depending on the substructures that you're observing here. This has some, difficulties because there is other mechanisms that you can activate to produce very similar substructures in disks. And there is another extra difficulty here is that, usually these things are very compact, very close to the center of the region. So what people are currently doing is instead of looking too much into the dust, they're also looking into the gas disk structure, which allows us to basically trace like the bulk of the material in the protoplanetary disk. So that's the other thing that I wanted to point out here. ALMA also gives us access to very high precision analysis of the disk kinematics, an entirely new dimension that was not possible before. So what you're seeing here is just the channel maps of 4 different protoplanetary disks. And as you progress in velocity here from one side to the other side, what you're seeing is just kind of the rotation paths. And so some emission is tracing the part of the disk that's moving towards the observer, and the other part of the emission is tracing a material that's moving, that's receding from the observer. And so, over the past few years, we have dedicated a lot of effort to try and understand these kinematic fields or the dynamical structure of disks. And we're, pretty happy to say that we can, nail down perturbations in these disks on the order of 10 to 20 meters per second, which may not sound too exciting to people like Jennifer, but 10 to 20 meters per second is really high precision for ALMA studies, and in particular to try and infer the presence of Jupiter mass planets embedded in these disks. Okay, so this is kind of the area of my main area of expertise, and you can, reveal by modeling these channel maps here, you can predict or quantify as well what the perturbation field of a given protoplanetary disk will look like. This is actual data, by the way. So this is the disk of HT135344b with, really compelling substructures, things that appear to be like Doppler flips, highly localized perturbations, potentially related to an embedded planet in there. And then you also have other types of sources exhibiting more like large scale substructures, this beautiful spiral here, which at the same time may be caused by planets. But, like using these combined data, substructures in the dust and in the gas, ALMA is allowing us to, to start, producing this kind of population studies of properties relating things like planet mass and orbital semi-major axis to try and reproduce those substructures that I just showed you. And people are starting to, make relationships between young protoplanet properties to the properties of fully informed, mature exoplanets. But the system that I want to focus on today is this one here, HT163296, which in the context of kinematic detections of planets was actually the one that pioneered this subfield of detection of protoplanets. Out of the 3 stars here, out of the 3 points here, which point to the kinematic planetary signatures, the first 2 actually come from this system. So it's clearly a very significant system in the field. And I will say that we already have a handful of additional systems here. This plot is outdated by 2 years right now. But yeah, this is the system that I will be focusing on for the remainder of this talk. So what happens in HT163296 is that, in 2018, the group of Christophe Pant et al. Detected this little wiggle in multiple channel maps of this system. And they basically note the scale, by the way. This is probably 6 arc seconds here and here. And at the distance of this system, this is 100 parsecs away from Earth. This means 600 a year in physical extent. So this is pretty massive, pretty large protoplanetary disk. And so they detected this kink-like structure. You can see that it's relatively localized. Actually looks pretty localized, because if you look at the other kind of side of the disk, you actually can follow this smooth trajectory here, but this kind of thunderbolt-like structure is quite particular, quite specific to that area of the disk. So what they did was, okay, so if that's highly localized, it's also highly likely that this is produced by an embedded protoplanet. They tried to forward model this using different grades of simulations, varying different planet masses, and they suggested or reported that this kink-like structure was likely driven by a 2 Jupiter mass planet embedded in this region of the disk. And so this also motivated part of my PhD work, because we wanted to provide, like a more quantitative way to analyze these substructures, and in particular quantify what will be the velocity perturbations required to produce these kink-like structures in the channel maps. On one hand. And on the other hand, we also wanted to quantify or use these localized perturbations to quantify what will be the planet location and the potential planet mass driving these perturbations to the velocity field of disks. And so we applied these new methodologies to the disk of HT163296, and we observed in 2023 that in this, the planet associated with the king-like structure was indeed related to a localized perturbation in the velocities, as you can see in these contours here. And it was sitting on top of a more like elongated substructure, kind of a filamentary structure in there. But then if you look more closely, we were also detecting a highly localized perturbation in the innermost regions of this protoplanetary disk, both in 12CO, in red to blue colors, and from pink into green colors in 13CO. So we were seeing the localized perturbation at a very specific location in the disk in 2 different molecular tracers. And we again tried to forward model this signal, by measuring the amplitude of these perturbations. You can say something about the mass as well, right? So we came up with this value here at Jupiter mass planets for this perturbation, and it's located at a radial separation of 94 AU, which is why we're calling this planet P94. So what we wanted to do more recently was, okay, now that we have this system, which is apparently very interesting for planet-disk interaction studies, what happens when you study other types of molecular tracers? This is an added value that ALMA provides us with, which is, okay, so if you have different molecular line observations, you can use this information to also kind of produce like a 3-dimensional tomographic study of your disk, because different molecular lines, they will emit from different regions in the disk depending on their excitation properties, and also depending on things like temperature, structure, and irradiation fields. So one of the things that we wanted to do was, okay, now let's revisit the disk of HD 163296, now including more molecular lines. And we came up with studies of disk mass, disk turbulence using different tracers. But then I want to draw your attention to these 2 specific data sets coming from the ALMA Large Program maps released in 2021 with an angular resolution of 0.15 arc seconds, which at the distance of this source translates to 15 AU, and a channel spacing in this case of 0.2 kilometers per second. So what I want to draw your attention here is what you're seeing in the first 3 rows is HCN emission for this rotational transition, 3 to 2, just centered at different hyperfine transitions within this group. And in the final row, you're seeing C2H emission for blue shifted channels, namely emission tracing material moving towards the observer, and red shifted channels on the other side. So apparently everything seems normal here, right? Except perhaps for this particular substructure, this kind of gap in the middle of the disk. But then if you look more closely, you will see straight away this little blob here. It turns out that this blob is actually overlapping with P94, our kinematic planets that we detected a few years ago. And so this was very exciting for us, because this is kind of something that people like Clips et al. In 2015 had already predicted, in the sense that if you have a localized source hitting your material, and in particular for molecules like HCN, then you will have, HCN molecules being released from dust grains. Originally, they were frozen out into dust grains because of the low temperatures, and now you're able to release those into the gas phase, and you can observe this very prominently. And these are other predictions that came out this year, completely similar to what we're observing in our channel maps here. And so what you can do is, okay, so now that we see that this is overlapping in 2 dimensions, what happens with the 3rd dimension? Is this like warm bubble also emitting from the midplane layers where we expect the planet to be located? Or is it rather as the atmospheric layers of the disk? So what we did in this regard was, okay, let's try to model the entire circumstellar disk structure, and then try to infer what the vertical location of the signal actually is. And so to do this, I'm going to go faster here because I don't have much time. We used my code disk miner to understand the dynamical and physical structure of the disk, but also to understand, like I was saying, the vertical structure of it. So this is in this case, the elevation of the emission surface for HCN as function of radius. And we inferred on average that the set over of that emission structure is 0.2, which translates to like 10 degrees with respect to the midplane. And then we also infer some vertical bumps here, and the radial structure is also quite perturbed. But the point here being that once you have inferred the vertical structure of your overall circumstellar disk, you can use this information to try and deproject the emission that you have in your channel map, in particular the one where you have the P94 signal. And so if you do this correctly, and if you inferred the circumstellar disk structure appropriately and the geometrical parameters as well, then you will expect that your emission will fall very closely to the isovelocity contour that's tracing Keplerian rotation, which in this case is the yellow line here. And this is actually true for the majority of the circumstellar disk structure, but it's not true for the planet signal here. So this indicates that there is an offset, an inherent offset between the planet signal and the circumstellar disk position in the vertical direction. And so what you can do is, okay, now let's try the same thing, but assuming that the emission surface height of the planet signal is actually at the midplane. When you do that, you actually find that the signal is quite intersecting with the isovelocity contour expected from Keplerian rotation. So this to us is speaking to a coincidence, not only in 2 dimensions, radial and azimuthal location of the planet signal with the kinematic planet, but also a coincidence in vertical location. So this is kind of the summary of the circumstellar disk structure versus planet signal here. And then you can keep pushing forward, to try to isolate the spectrum of the signal, comparing the 2 different sides of the disk, where you have the signals here, circumstellar disk plus planet signal. And then you by using this information from the geometry of your disk, you can actually try to filter out the circumstellar disk contribution to the final spectra. And so what we're doing here is just, okay, we isolate the signal. It's a very significant bump here, this is CSD plus planets contribution. And then, you can use this information to try and do some characterization of the properties here, right? So dynamics, structure of the CPD in principle here, if we assume that this is a CPD structure, you can actually try to infer different properties, including planet mass, CPD radius, gas temperatures, and stuff like that. So this is what we're trying to do here. We generated a grid of models for different temperatures, assuming these 2 factors here. And then we came up with this relationship where you can correlate CPD radius as a function of planet masses. And if you additionally put theoretical constraints, you can actually narrow down the properties that are most likely to occur here. And I would like to point out that this is very consistent with the planet mass that we were inferring at the beginning from kinematic detections. So I'll leave it here because I think I'm well over time. But yeah, these are my summary and conclusions. Thank you very much.
Time for one quick question while the next speaker comes up.
So thank you for a very interesting talk. I'm curious about how do you roll out instabilities, for example, in interpreting the velocity kink?
Yeah, so that's probably a question for next symposium, actually. But that's a very interesting one. That's something that we're working on actively within the XO-ALMA framework, because there's multiple observables that one can use. Not only do you have kinematic information, but you also have things like line widths and temperatures. So we're trying to combine all this information together from line profiles to build like a coherent picture and try to unambiguously say this is truly a kinematic planet detection versus this is probably disk instabilities. Trying to combine different pieces of information. And what we're seeing right now is that it's possible to do that, disentangle those different mechanisms. Yeah.
Okay. Is it working? Did you switch it to the top?
No.
Now it is.
No.
Okay. Our next speaker is Changhong Se, and giant planet formation.
Hello, everyone. I'm Changhong Se. So today I'm going to talk about the onset of protostellar substructures and planet formation.
So I will start with my talk with the famous HL tau image. So ALMA showed a lot of beautiful substructures with like rings and gaps in 10 years ago. And this is the latest version of the HL tau observed by Ian Stephens in 2023. So after 10 years, now we now see a lot of substructures in a lot of polar planetary disk, and we can start to do statistics. So it's important to point out that over the past 10 years, most of the previous studies predominantly target large luminous disk with more evolved disk with ages greater than 1 million years. So mostly class 2 disk. For example, the famous D-Sharp survey by Sean Andrews and also the Odisha survey. Until recently, there start to have some surveys to look at the youngest protostellar disk with ages less than 1 million years. These are like class 0, class 1 disk. So one ALMA large survey led by Ohashi in 2023, the EDIC survey. So they surveyed 20 disks shown on the right-hand side. And these are like class 0 and 1 disk. So they are very young. They have age like less than like 1 million years. And you can see that most of the disks are pretty smooth. So you don't see much substructures in them. So this could be telling us maybe substructures in younger disks are harder to find. And it's important to point out that until today, we don't really have a high angular resolution uniform search of these substructures for the youngest class 01 disk. However, studying them is very important because they tell us how early does these substructures form, and as a corollary, how early planet formation begins. So to talk about like tracing the evolution of polar planetary disk, it's important to look at how the protostellar system evolved. So for the youngest sources, because it's deeply embedded inside envelope, we cannot plot it on an HI diagram and then fit isochrones to get the ages. So what we use is we look at the change in SED. So for the younger sources, you have protostellar cores, and as they start to collapse, and due to the conservation of angular momentum and centrifugal force, you will form like a disk. And in the class 0 phase, because the envelope is very thick, so if you look at the class 0 SED, you'll just see a black body of the envelope. And as it evolves, the protostellar outflow also widens, the density of the envelope will drops, and you'll start to see like the infrared emission from the disk, as well as the central protostar. So the emission from the disk and the central protostar will give out like the infrared emission around like 1 to a few hundreds microns. And as it evolves, as the protostellar system evolves, in class 1, we will start to see the infrared access from the disk, as well as some black body emission from the central protostar. So here is a big, like, general picture about like the polar planetary systems. So as you can see, early on, you'll just see the thermal dust emission from the cold envelope, and then over time, you'll start to see more infrared emission from both the disk and the star, and that's how the SED changes. So we use the change of the SED to trace the age of the protostellar system. So to quantify the change in SED, we use something called bolometric temperature. So bolometric temperature is not really a temperature. It's the temperature of a black body having the same mean frequency as the observed continuous spectrum. So imagine looking at the different SEDs. Let's say if you just like fit a black body curve to it to get a number, and then this is just a way to quantify the whole SED into one single number. And so as the protostellar system evolves, you'll see the bolometric temperature will also increase. So now we talk about how we trace the evolution of the protostat system. Then now we can start to see when the substructures starts to form. So introducing our campus survey. So here are our campus team: me, Hector, Ashwarya, Jaime, Maria Jose, Dominique, Mike, Dalham, and Diego. So we use ALMA to observe nearly all the embedded protostars in 7 nearby molecular clouds: Comedian 1, Comedian 2, Ophiuchus, Ophiuchus North, Aquarium, Corona Australis, and Serpens. This is from the Dalham et al. 2015 catalog, which is the Spitzer Legacy Survey, C2D, and the Gold Belt Survey. So we cover the full class 0, class 1, flat spectrum sources, and early class 2 sources with bolometric temperature less than 1,900 Kelvin. So in total, we detected 184 disks. And out of those 184 disks, 90 of them have an angular resolution around 15 AU. So here shows our campus survey comparison with the D-Sharp, OD-Shine, E-Disk. So the D-Sharp, OD-Shine, E-Disk survey, they are observed at much higher angular resolution, around 4 to 7 AU. Our angular resolution, linear resolution is around 15 AU, but we have much higher amount of sources, around 90 disks as compared to 10 to 20 disks for those higher angular resolution surveys. So with these 90 disks, one important thing about our survey is that it's done uniformly. We observe the clouds uniformly. We're not trying to select the brightest and biggest disk. So with this uniform survey, we can start to conduct the statistical search for the protostatic disk substructures, and then try to see when it starts to form. So here shows some of the substructures detected in our survey with like rings and gaps, and I ordered them by age from class 1 flat to class 2. And out of our samples, we found that disks with multiple rings morphology are generally larger than other types of morphology, for example, like a ring. This could be something like intrinsic, that larger disks can develop multiple rings, or this could be due to observational bias, that it's hard to detect multiple rings in smaller disks. And interestingly, we found that there seems to be two populations of these substructures. If you look at all the substructures, there's one type that shows like central cavity, the other type is centrally filled. And we see like both of them from like early class 1 all the way to class 2. And interestingly, if you look at all the multiple ring systems, they tend to be centrally filled. If you look at like all the, even in higher angular resolution, you still see like multiple ring systems tend to be centrally filled. You don't see a huge central cavity in multiple ring systems. We don't really know why, but that's something we're interested to figure out in the future. So to study the onset of substructures, it's important to take into account of effective resolution problem. So as shown by Bell 2023, majority of the disks without substructures have been observed at low effective angular resolution. So in other words, you need to have enough samplings across your disk in order to see substructures. So we select the samples such that the disk is sampled with at least 4 beams, 4 resolution across. And it's also important to consider the inclination angles, which we take out edge on disk because it's difficult to see substructures in edge on disk. So here is our main result. How early does this substructures form? On the y-axis shows the disk mass and disk radius. And this is the blue shows the one with substructure, the orange without substructure, and the black cross is compact disk. So they're not well resolved. Their disk diameter is less than 4 beams. And so in this pic, on the x-axis shows the bolometric temperature. So this is the tracing the evolution age. So we see substructures start to show around 200 Kelvin, which is around like 0.2 to 0.3 million years. So the bolometric temperature is adopted by the EHUBS group. So it includes the Herschel measurement, but they didn't do the extinction correction for the infrared part. So this is the lower limit. And later I'll show the upper limit. So here is the upper limit. And you can see that similar plot, and you start to see substructures around T-ball around 400 Kelvin, which is around 0.3 to 0.4 million years. So by plotting the substructure detection rate for both of the bolometric temperature measurements, you can see that we start to see substructures around 200 to 400 Kelvin. So this is very interesting because this shows that substructures develop in early class 1, not between class 1 and class 2. So in early class 1, the protostar is still accreting its mass. So it's still building up. So this is telling us the conventional picture of having like you form the protoplanet, you form the protostar first, and then you form planets later. It's not exactly correct. You're actually forming the protostar and the planets together. They're growing and evolving at the same time since early class 1, which is around like 0.2 to 0.4 million years. And interestingly, we found like we look at the linear resolution and we didn't see any substructures for class 0. So this could be like during the early times, the substructures are very small, embedded in the disk, or maybe the optical depth is much higher. So to sum up, we found like these substructures evolve rapidly between class 0 and class 1 with ages of between 0.2 to 0.4 million years. And this is suggesting that planets and stars are forming very early on together and growing and evolving at the same time. And this, I'll leave my conclusion slide up and take questions. Thank you.
A few minutes for questions. So
is there any evidence in any of these type 1 systems besides substructures that there may be a planet?
Oh, that's a very good question. So also a very difficult one. So we see substructures. It's very hard to know whether they're caused by a planet or due to instabilities. But we know once the substructure starts to form, because of like a pressure maximum and a high concentration of dust, this will like trigger planet formation. So it could be like early on, the earliest substructures are formed by instabilities or disk wind. And once you still start to have like planets, then planets can also generate a second generation of substructures. These are like different ideas to explore, but right now we cannot really tell. We need like line data and start to like establish examples of like which mechanism create what kind of substructures.
Great talk. So I'm interested in the like donut versus egg situation. So what is the size of the like empty region around the star?
So the empty region is around. So that's like around.
Is it like tens of AU? Is it
tens of AU?
Okay.
Our linear resolution 15 AU, so tens of AU.
Okay. Yeah.
So you can expect to fit the like inner solar system in there.
Is there any correlation with like the bolometric temperature or like any property of the star that you think might be at the center?
Yeah, that's a very good question. So one of the reasons why we start to separate them into two is to test the idea of whether substructures are evolutionary linked. So there's a group by Cieza et al. In 2019. They suggest all the substructures are evolutionary linked, and they can be explained by radial drift and with a planet. So they separate them into different stages, just like star formation, from stage 1 to 5. And to test this theory, we look at the features of stages and realize that early on, you can see it's mostly central field, and over time, it shows a central cavity. So if this theory, evolutionary theory, is correct, then we expect to see like all the donuts as being more evolved, and the one central field sources early on. And we did like a test, seeing like the cavity type versus the field type as a function of bolometric temperature, and we see that it's basically flat. And so this is suggesting that the substructure we see are not necessarily or evolutionary linked. They could be created by different populations. They could have different populations created by different mechanisms. Or if they're evolutionary linked, that means they evolve very rapidly and can be triggered at different times.
Okay, we actually do have to move on in the interest of time, but there are more coffee breaks, so you can keep bugging him if you have more questions.
Okay.
Thank our speaker one more time. Okay, our penultimate speaker of this session is Charles Law, who's going to continue telling us about giant planet formation through disks.
All right, thanks for the introduction. Can you hear me okay? All right, great. Hi, everybody. My name is Charles Law. So I'm a third and final year Sagan Fellow at the University of Virginia. And I just want to thank the organizers. This was a really wonderful symposium, and they've all really been wonderful. So today I want to continue the theme of protoplanetary disks, and I want to convince you about a special type of those disks. And this is a special geometry, those that are facing us in an edge-on orientation, as you can perhaps already see here. So I do have to slightly amend my title. I said this was the sharpest view of the largest disk. This has since been revised to the second largest protoplanetary disk, which I still think is a special system. If you're curious what the largest is, ask me afterwards. But so just to set the stage, what I want to emphasize is that disks are a natural byproduct of the star formation process, as you see here in a plot that I'm sure you've seen many times, where you start with your molecular cloud, collapse down, and eventually you end up in a protoplanetary disk phase, which is the direct precursor to forming a fully fledged planetary system. And it's exactly this phase that I'm most interested in for that reason, because this is the really last stage when we have abundant reservoirs of gas and dust and ice that eventually end up going into your planetary system and deciding the initial conditions for forming your planets. And I just want to stress that this is a particularly great time, because as I just mentioned, there's these three dominant components in your disk that we should care about: dust, ice, and gas. And we are at a time now when we have facilities where we're able to observationally assess and characterize each one of these. And so we're moving towards a comprehensive picture of disk composition, really, which is incredibly important to connect with exoplanetary environments. So particularly it's ALMA gets us access to the gas and dust, and JWST gets us access to the ice and a little bit of the gas as well. OK, and these disks are really exciting because in them, we know planets are actively forming here. And if we observe them, we can really see the environment which they're actively assembling. They're taking the gas, they're taking the dust, they're putting it together, and actually making an active planet here. The challenge is that these disks are quite complicated. So here is a quick schematic of a cross-section of a protoplanetary disk. And what you see here is the presence of pretty steep gradients in lots of things, in the gas density as well as the gas temperature here. You can see the orders of magnitude that we're talking about. All of this is happening over relatively small scales. So if you look in the radial dimension here, this is maybe a few 100 AU or so. And in the vertical dimension, it's a few tens of AU. So what this does is it puts pretty stringent observational requirements if we really want to unpack what's going on the small scales here. And we absolutely need to do that because the disk structure imprints itself on the type of planets that you want to form. And very quick example. For instance, imagine you have a location in your disks when you go from having ice to gas based on the temperature, and say that's water. At that location, so what we call the water snow line, exterior to that, you're going to have icy bodies, icy planetesimals, and interior to that, you might have rocky bodies. And so when you end up forming your solar system, you might end up having this imprint in your final planetary system. Of course, it's much more complicated in detail than this, but just one mapping where we'd like to understand the structure to understand what kinds of system architectures are coming out of these disks. Today, I want to specifically focus on this dimension here, which is the radial, the vertical dimension rather than the radial. Andre showed some very nice radial maps. The vertical dimension is a bit more challenging and a bit less characterized. Again, as you can see, this is a few tens of AU or so. We know that these disks have a vertical extent, and you can see this really beautiful image here with HST of one of these edge-on protoplanetary disks. The disk midplane is sitting right here, and this is scattered light coming from both the top and the bottom surface here. So we know that they have a vertical extent, and we want to understand how to characterize that. So the question that I want to ask is, what is the ALMA view? What can ALMA tell us here about the disk vertical extent? And I should just preface what I'm going to show. Anything that's gas is typically coming from an upper elevated layer. It's not coming directly from the midplane here. It's coming from a warm molecular zone, because we're looking at gas emission. The temperatures need to be warm enough. By the time we're down here, we're mostly in ice, and we're not going to see that with an interferometer like ALMA. And if we look at actual real observations, we in fact see this structure, where you can see in the middle here, you have, this is the disk midplane. This is emission in 12CO gas. And you can see very much there's this butterfly-like pattern from the upper surface, which is this one, and then the lower surface, which is this one right here. And by the time you get down here, it's a bit too cold, and a lot of the gas has gone away, and it's in ice. So I've been very interested in general in understanding the height and the distribution of the vertical dimension in these disks. So I'm just showing one code that I was involved in fitting this. We can apply it to all kinds of disks as long as you have good enough angular resolution. Andres' code, Disk Miner, also. There's many of these codes that are out there to help us unpack different geometries, different types of systems. But what I just want to convince you, or at least show here, is that this information, being able to map out the height of your molecular gas, encodes a huge amount of information that you might care about. It tells you something about the gas temperature, its density, the pressure. It tells you something about the disk mass, the elemental abundance, and particularly how much carbon you have. You need it if you want to measure turbulence. You need it if you want to measure perturbations, as was already shown earlier on, due to planets. And in fact, if you choose the right tracer, you can even measure the UV field right at the upper disk layer. So by measuring this, the distribution vertically of gas in your disk, you get a ton of information. So with that as a preface, I want to now move to the second largest protoplanetary disk. It has a funny name. It's called Gomez's hamburger because of this sort of shape here. It looks like a sandwich. This is a nearish 250 parsecs system around an A-type star. And initially, there was some confusion about what this source actually was, considering how large it is. But submillimeter array observations about more than 10 years ago now did show that there is the characteristic signature of Keplerian rotating gas. So here's the blue side, and then as you move here, this is the red side. What you're seeing in the white here is scattered light coming from small dust, so submicron and micron-sized dust that is scattering the light in the optical. This system is huge, exceptionally large. The extent here is around 3,000 AU, and in this direction, it's around 600 AU. So this is a huge, huge disk. If you compare this to the size of our solar system, this is something entirely different. But because it has this very nice edge-on orientation and its size is so large, particularly in the vertical dimension, 600 AU, it really is a wonderful laboratory to really peer in and understand its vertical structure. What's more is this initial paper from more than 10 years ago with SMA data was able to take a position velocity diagram of the gas rotation. And this is what they found here. So if you're not familiar with these, this is the shape that you'd get with Keplerian rotation. So this helped them confirm that it was, in fact, a protoplanetary disk. But what they identified was a asymmetry right here. You had more emission sitting right here than you did on the other side. And at the time, they just called this GoHam-B, some generic clump. You could wildly speculate that this was a protoplanet forming there, but really it is just some clump. You have more emission happening in this part of the disk. And if you go back spatially, it's sitting somewhere around here. So that's what we knew. This is exciting because if it is actually a planet, you're at 500 AU. This is very much a wide separation giant planet, maybe in the beginning stages of forming. So gives us some idea about gravitational instability, perhaps. So I want to show you some of the new ALMA data, our new sharp eyes on this disk. So here again, just a schematic. Here's where the disk is going to be oriented. Star is in the center. Here's a dark midplane. And now I'm just going to flash through some different molecules. So here you go. Here's the 12CO. Just a fantastically beautiful image. You can see both the upper and the lower surfaces here. This is our spatial resolution. This is our synthesized beam size. So we have an amazing resolution to see the full vertical and radial extent. I can now flash the 13CO. Same structure. Now the layers have moved slightly closer together. And then here is a CS. So we can really just do sort of a chemical mapping and see vertical stratification in the molecular glass directly by looking at these edge-on systems. And the midplane in all cases would be right here. So just to very quickly walk you through the anatomy of one of these edge-on disks for those that aren't used to looking at this. In the background here is the scattered light, small dust coming from Hubble. Here is the dust from ALMA, the millimeter-sized particles. This is the material you typically associate with forming planets that has settled down to the midplane. And in fact, it has. You can see right here, the small dust is elevated and coupled with a gas, and all of the larger dust particles are sitting right here in the disk midplane. So we can see both of these components very nicely and directly because this is an edge-on system. We can then overlay the 12CO gas here, and it matches pretty well. So the gas is pretty much tracing those small dust particles. This makes sense. The small dust is coupled with the gas, and so they're pretty much at the same vertical height. And then we can do the same thing now with 13CO, and we can see that the layers have moved slightly closer together, slightly closer to the midplane. 13CO gas is in general a little less abundant than the 12CO, and so because of optical depth effects and temperature structure effects, we're moving closer to the midplane. Okay, so there's some neat things. There are many neat things that you can do with this kind of data. I'll just show you one quick example. Using velocity-based reconstruction methods, we have very high, at least for ALMA, velocity resolutions. We can then go ahead and reconstruct the temperature structure of this disk as a function of radius and height here. This is the previous submillimeter array observations. Here is the beam size, and here's what happens when you move to ALMA. You improve dramatically, very much smaller beam size, and you can very clearly see the upper surface here in 12CO and the 13CO temperature here. You might notice that there is a bit of just scatter here in the background, and this is because our observations are so sensitive. You need to actually get everything right. You need to know exactly the inclination of your disk. You know exactly the position angle. And you need to then feed those into the reconstruction methods, which haven't always been as sensitive before because we haven't had data this good. So I'm working with a graduate student at MIT, Jensen Lawrence, who's actually improving this right now, trying to put in all these geometric parameters to help get rid of some of this extra noise here. And he's using that to do a lot of extra cool science that will be coming out soon. Okay, so the very last thing I want to wrap up with is what about that Goham B? What about that clump in the south that was supposed to be somewhere here? So when we looked at the ALMA data, we found something pretty interesting, and that was this, the detection of SO, so sulfur monoxide. And it's shown here in the colors right here, and then the orange is the millimeter dust. So again, this is like the midplane right here. And we're only seeing emission from this SO molecule on one side of the disk, which is extremely strange. It's entirely localized to one side. And in the north-south direction, you have an asymmetry. You have the brightest blob of emission right here. And then as you move up to the north of the disk, it gets fainter and fainter. And so we absolutely didn't expect to see something like this. And it's led to more questions than we have answers right now. So this is very much work in progress. But one speculative explanation for this would be that you had some localized heating source, perhaps a protoplanet or just perhaps material falling in very vigorously and clumping together, that is at this point heating up the surrounding gas, liberating SO molecules that are on ice, putting them into the gas phase, and then the gas is just rotating away. It's just in Keplerian rotation, it starts rotating around your disk, and then it loses its access to the local heating source, and it just slowly freezes back out onto the ice grains. But if we're working out the details of that right now, but that's a very possible explanation for what we're seeing, and it would explain why we're only seeing it on one side of the disk and not the other here. Also, there's a dust asymmetry here. So if you look in this direction here, this is a little more elongated. So something is definitely happening in stirring things up in the southern portion of the disk here. Okay, and so then I'll wrap up by just saying that the future is bright here. This is really the first source that we can do. Where there's a large program now that's going to do this for 9 sources, including GoHam. So everything that I showed you will be repeated 9 times with even more chemical data. And all of these sources will have JWST imaging and JWST ice data. So we'll have an entire inventory of 9 sources, gas, dust, and ice, where we can really put this together. So with that, I'll leave up my summary. I hope I've convinced you that edge-on disks are pretty interesting, and happy to take questions.
You have time for a couple questions.
So for the SO, does it correlate at all with the like dusts, like bump or like overdensity that you were seeing earlier?
Oh, relatively, yeah. I mean, it's not exactly overlapping, but yes, they're in the same vicinity, yes. And we couldn't tell exactly, so if the local heating source was like right in here, you might be losing a bit of it because optical depth effect through the dust. And you might just be seeing its effect come out here, or whatever it is might actually be right here, separated from the dust. So the exact position of whatever is driving this is a little hard to get at. But with our temperature reconstructions, once we get them sort of refined, we might be able to pick that out.
So do you have a handle on what the protostellar properties are in the center of this very big disk?
It's hard, and it's distance dependent. So I can give you basically a mass value that scales with distance. And so if you believe the distance that is so far quoted, which is a little fraught because of it's an edge-on disk, so it's hard, but it's at least 3 solar masses. It could be more, it could be less, depending on how far away this is. But it's an A-type. We know it's A-type. It's a massive system. Edge-on sources are not the best to get the perfect mass estimates. Yeah.
Last question here, and then we'll have to move on to our next speaker.
Thanks for a very interesting talk. I'm curious about how do you form the disk that's 3,000 AU in size?
That's a great question. It appears to be stable. So one of the goals of this is we'll actually be able to comment on the degree of stability. It looks like the disk to mass ratio is anywhere from like 10 to 20% in this case. It appears stable, right? I mean, there's a little asymmetry here, but you don't see anything really indicative of this thing is totally collapsing or dispersing. So we know it exists, but yeah.
Okay, let's thank our speaker one last time.
Okay.
Give it just a second. There it goes. Okay, our last speaker of this session is Xingjia Zhang, and whenever you're ready, take it away.
Thanks for the introduction. Can you hear me okay? Okay, so my talk is about shadow-induced warp in protoplanetary disk, and the 2 words you need to remember are shadow and warps. So let's get started. This is a protoplanetary disk, and the previous 3 talks have explained very well about what is a disk, but I still want to emphasize that at the center of the disk, there is at least 1 star. And this star is the primary heating source of the outer disk. And there are also gas accreting through the star, onto the star through the magnetospherical accretion. And then at this region, at the very inner disk, there is only gas component because the temperature there is so high that sublimate the dust. And at the fraction of AU, and depending on the stellar mass, the dust will finally condensate and form a dust inner ring. And then the outer disk, there are a lot of things going on, and you have already seen a lot of many interesting pictures of them. And I would argue that this is not a complete picture yet, because there are many evidence now that the disk is warped, or the inner part of the disk and the outer part of the disk are misaligned. There are many lines of evidence. First, from Kepler K2 and TASS data, many of the pre-main sequence stars have these dipping events in the light curves. And the way to explain these dipping events is that there is something inner disk very close to the star in the edge-on configuration that periodically blocking the stellar light. And if you expect the disk is a coplanar configuration, the outer ALMA disk should also be sort of adjunct. But in fact, the outer disk have almost isotropic distribution, and many of them are exactly almost face-on. There are also recent paper also using TASS data where they measure the mutual inclination between the stellar spin axis and the outer ALMA disk. And they find that at least a third of these stars have mutual inclination greater than 15 degrees. And this is also imprinted in their titles. Another very strong evidence comes from the near-infrared scatter lights, where people see shadows. And there are two categories. One is these very wide shadows crossing half of the disk, and the other type is these narrow shadows, but there are two in pairs. And the shadow can be explained by a misaligned inner disk, and depending on how misaligned they are, it can be either a very wide shadow, or when the inner disk is almost polar to the outer disk, it can create these narrow two shadows. And this has also been confirmed in the near-infrared interferometry, where you indeed reconstruct the inner disk and constrain their inclination to be very misaligned with the outer disk. And this is very similar to what Charles were talking about, the adjunct disk observed by JWST. And this is the second largest protoplanetary disk Charles talked about. So in this sample by Villanovi, 15 out of 20 of them shows this so-called lateral asymmetry, which means that the top of the surface of the scattering surface has some symmetry with the bottom of the scattering surface. And that can also be explained by a misaligned inner disk. And you don't need a very high misalignment, even at the best geometry. 3 degrees of misalignment can produce this very strong, visible lateral asymmetry. Also from JWST and from previous space-time observations, people detect the so-called seesaw variability. It is that if your shorter wavelength flux increases, the longer wavelength flux will decreases. And you can also use a precessing inner disk to well reproduce this phenomenon. So given a lot of observations, the question I want to ask is that whether this shadowing or misalignment have dynamical effects to the outer protoplanetary disk. So I used radiation hydro simulations with the ray tracing from the star and the radiated transfer of the disk, this self-emission, and I used this transition disk configuration. Basically, I have an inner disk that provides attenuation, and then there is this empty space called cavity, which is shown in Chen Han's talk. This bagel? Yeah, this bagel part and the outer disk, which can be detected by ALMA. And I have two mutual inclination, 30 degree and 90 degree. This is what I presented last year in the symposium. When you have a polar configuration, when your temperature becomes lower at the shadow, you create two spiral arms, and they can accrete into the inner disk and results to alpha equals to 10 to the negative 2, very strong accretion. And then you can also reproduce these kind of observations. And the topic today is what about mildly inclined disk? This is a more generic situation. And let's see what's going on. So on the top left, it shows the radiation the outer disk receives. At the initial condition, there is no shadow. The shadow is not turned on yet. And so it's all irradiated. And the disk is a flat disk. We set it as the initial condition. It's perpendicular to the z direction. But as I turn on the shadow, you see the shadow there. And the disk is warped immediately. After the initial relaxation phase, you can see that the inner disk is tilted towards the direction of the shadow, whereas the outer disk is tilting in the other direction to sort of conserve the angular momentum. And you can indicate the tilt from this dotted black line, which shows the twist of the disk. So to summarize, in the initial condition, the disk is in a coplanar configuration, but once you turn on this shadow, the disk is tilted, and it's not only tilted, but the inner part of the outer disk and the outer part of the outer disk warps in the other direction. Eventually, it reaches a quasi-steady state at a fraction of a million years. And in the meantime, you also see strong accretion. There are spirals accreting into the inner disk, and there are more material in the inner disk than the initial condition. We can quantify this by measuring the tilt, beta, twist, gamma, and the warp amplitude per psi. You can also see that the inner part of the outer disk is tilting towards the 30-degree inclination, which is the inclination of the shadow. And the twist of the outer disk is aligning with this 90-degree shadow's twist. But then when you go to the outer part of the disk, the twist change sign. And that means the outer part of the outer disk has a strong twist to the inner part of the outer disk, so they have very strong mutual inclination. And we can also quantify the accretion by measuring the Reynolds stress. And you can see that compared to the polar configuration, this 30-degree misaligned case have 100 times stronger accretion, and this alpha can be as high as 1. And the accretion rate is also 100 times higher. And let's understand why this is happening by looking at the vertical disk structure. As you can tell, this is very far from the Gaussian in the vertical direction. And in the azimuthal direction, when you follow the scale height, it varies twice in orbit. And there are two locations here and here that have very narrow vertical extent. And this is where the place where the disk is squeezed by the shocks. And you can see the shocks in the temperature structure here by this white line at very cold midplane. And when you look at a streamline, it becomes more clear. You see the gas is impinging the inner disk and compress the very high density region. But because the density is so high, it meets the shocks and it bounces back. And then after a while, it bounces back again. So you have this twice per orbit compression. And this is not the first time people see this in the simulation. Actually, in previous recent GRMHD simulation around black hole disks, you see this, and they call this nozzle shocks, and where they also see very strong accretion that leads to the accretion alpha as high as 1. So we can also produce a lot of very significant kinematic signatures for AMA observations, but we want to understand why it warps. So we suspect it is the temperature structure that warps a disk. And we prescribe the pure hydrodynamical simulations with the temperature that results from the shadow. And indeed, we found a similar level of the warps. But we still want to know what's the exact modes that leads to the warp. So we decompose the temperature structures using Fourier Hermite series. And the most important mode is this M1N1 mode. It means that the top and the bottom of the disk are anti-symmetric. And in the azimuth, there's this so-called dipole mode. And we can also decompose different mutual inclinations onto this series. And you can see that this mode is strong anywhere between 3 to 30 mutual inclination degree. And then we also run a simulation with just this mode, m equals to 1, n equals to 1. And they can almost reproduce the beta tilt and twist of a full shadow simulation. So we identify that it is this mode that drives the warp. When you subtract these two simulations, the tilt and the twist are similar, but the leftover becomes the residual of the m equals to 2 component, which drives two-arm spirals. I guess I will just leave my summarized slides here and I've open floor for questions.
Yeah.
Thanks for a very interesting talk. So you were kind of getting at this, I think, with the last part of your talk, but I was kind of wondering, in black hole accretion disks, you can have a misaligned disk when the spin of the black hole is misaligned with the inner accretion disk, and here you don't have that, presumably, so what's the mechanism for causing the warp in the first place?
Yeah.
To be thermally driven?
That's a very good question. What's going on here? The disk should not warp, but it warps. So the basic, if the disk warps, it means that it has the angular momentum from not just the z direction, but also the x and y direction. But the disk does not have this angular momentum as the initial condition. So there must be something going on. One explanation is that you can transport angular momentum between the inner and outer disk, and somehow in total they still conserve the angular momentum, which is still also not the case here. So what we measure is that there are a significant amount of angular momentum flowing through the upper and lower boundary of the disk, even though our simulation domain is extending to almost the pole, like 80 degrees, but still a lot of angular momentum is flowing. The Lx and Ly are flowing through. So it is both a very interesting observational problem and also theoretical problem. And we are working on the linear theory to understand this.
So some of these warps in the outer disk seem very extreme and interesting. So I'm curious if you could comment on the state of observations and if there are any disks out there or or other things that look anything like these really cool.
Yeah, so I think so, yeah. For example, but it's all still speculation. So one of my next projects is to work with Atlas on inferring the warp and first the temperature structure, asymmetric temperature structure, and its associated kinematic structures, and see whether we can find this kind of thing in the observations. I think observation is already there. It just needs someone to look into that. Also, there are also many rooms for the edge-on disks, was like this, the second large protoplanetary disk, where you could also look for these kind of signatures first from the temperature structure and then the associated kinematic and the symmetries.
Okay, I think I'm going to let us all go to coffee now, but as far as I know, all of you are sticking around, so feel free to keep the discussion going, but we'll come back at 4 still.